Okay, now here we are. Now you can convert this to meters per second. The wingsuit pilot into meters per second. So, um, the good old 0.447. So you're on your way. All right, so 16. If the wingsuit has a mass of 55 kilograms, what is her kinetic energy when traveling at 155 miles per hour? Now, you got to use your answer. So for problem 16, I know some of you are like, why does he do this to us? Because it's good for you. You don't just want to go through life without being tortured by math, do you? Or some of you probably thought, reading some of the essays, I think some of you thought you were done being tortured by math, but I guess not. All right, so anyway, so in problem 16, in number 16 in your notes, you've got to find the kinetic energy, which is 1/2 the mass that's listed there times the speed in meters per second you found in problem 15. I know I always do that. I get some complaints from students saying, "Why do you do?" Because physics is a building thing. You got to build on it. All right, that's the way it works. All right, I looked up in the G-force for a wingsuit jump when the parachute is opened, that exerts an acceleration of 2 Gs. What is 2 Gs in meters per second squared? Okay, this is just kind of review. I have to do this with my 210 students too. So 17. 1 G is 9.8 meters per second squared. So 2 Gs, I wonder what that is. All right, no biggie. You can do this. So if force is equal to mass times acceleration, aha. Now remember the G's that you got, that's the acceleration that slowed the person down. What is the force? So she's 50. So remember, problem 18, force is equal to mass times acceleration, and you found the acceleration in problem 17, which was built on problem 15. Oh no, actually it wasn't. It was just, I just kind of was built on problem 17. The acceleration you found in problem 17. Okay? 19. Knowing that the is force times distance, using our wingsuit jumper's kinetic energy and force, how far does she go before coming to a stop? Okay? Now, there's all kinds of, they actually hit the ground pretty hard. They don't come to a complete stop. So this is kind of a little bit bogus, but you did figure out a formula. All right. So in other words, you built the formula where you know the force, which is her mass times acceleration, is equal to her kinetic energy. Her mass times acceleration, which is her force, times the distance is equal to her kinetic energy. And you found her kinetic energy way back in problem 15. So you got to go back to that answer, or you can just calculate it again and go, okay, so she's going, so the kinetic energy, once again, is equal to 1/2 of 55 times her speed in miles in meters per second squared. And this is the only thing that's multiplied twice. Okay, so you found in 18, problem 18, or mass times acceleration, but you can just do it again. 55, so you could go force times distance is equal to 55 times 2Gs times D is equal to her kinetic energy that you got up here, and then divide. D would be the kinetic energy divided by her force that you got in problem 18. So it's basically what the answer you got in 15 divided by the answer you got in 18. All right? What's 20 say? Are we done? Are we about done? Please. It's time to stop is equal to the change in speed divided by the acceleration. Okay, I've got to do. All right, this is another one. Lucy, you got some explaining to do. All right, and I'll do it on this one. I don't care how long. This track might be a little bit long, but it's okay. The time to stop is equal to the change in speed divided by the acceleration. All right. So her final speed is 0. Her initial speed you calculated from the 150 miles per hour above. Speed in meters per second, her speed before in meters per second minus 0 is equal to what? Well, her initial speed. And the acceleration was, I gave you the 2 G's here. So the time is, some of you are going, wait a minute, what? Say what? All right, here you go. Now, it's not that hard. So, final velocity minus the initial velocity divided by the acceleration is equal to the time that it took her to stop. Okay? So the acceleration is, so in this one you might be going, well, wait a minute. 0 minus, well, at this juncture, I'm just going to go ahead and say, whatever it is. Some of you are going, man, I wish I hung in there to the, okay, so on. So 150 times 0.447, which gives us our speed. Oh, man, guys, see, it gives me this bullshit, 13 or, I don't want that kind of answer. I want my old calculator back. I want an engineering, there we go. Thank you, Jesus. Okay, 67.05. Now that makes sense to me. But 67.05, that's her meters per second, divided by the negative 19.6 G meters per second squared. So look what happens. The meters cancel. One of the seconds cancel. This second's all the way down here, so it comes up here, so you get the time. But it's negative over negative, so it's positive. Your seconds are always, so you can just take 67.05. I've messed with you enough. Divided by 19.6. And that should give you the time it took her to stop. Which you can kind of look at and go, oh, it's about 3.5 seconds. All right. Have fun with this. And I highly encourage you, if you skipped over some of the videos, go back and watch the sports videos. They're a lot of fun, and especially that little 60 minutes segment. It's about 13, 14 minutes long, and it's really cool. At least I found it to be cool, So, but anyway, out here, enjoy the debates if you're going to watch them. I'm going to get, like I told my daughter, no, I'm going to rewatch season 1 of Deadwood, I think. All right.